Thank you for watching this video. My name is Yusudo from Tokyo Institute of Technology. I'm going to talk about environmental sound segmentation utilizing a mask unit. In recent years, there has been a lot of research on automatic speech recognition and speech synthesis to enable human-robot interaction. In particular, various methods such as noise reduction, sound source localization, and separation have been developed in robot audition, with the aim of applying them to real-world environments. These methods have been developed and evaluated individually. However, in order to use these robots in a real-world environment, it is necessary to use these methods simultaneously. So they should be evaluated in an integrated manner. Therefore, we defined and evaluated the multiple tasks of section detection, sound source separation, and classification as a single task, environmental sound segmentation. I'll introduce some related works. Related works are divided into two approaches. The first approach is to cascade individual function blocks, such as sound source localization, separation, and classification. Each function block estimates the direction of arrival and separates the sound sources arriving from different directions using array signal processing techniques. However, cascades can result in the accumulation of errors generated at each function block. Because each function block is optimized individually, regardless of the overall performance, the output might not be optimal for subsequent blocks. Second approach is integrated approach using deep learning techniques. UNet, which is originally proposed for image semantic segmentation, has been proposed for vocal separation. This method is an integration of section detection, sound source separation, and classification. However, most previous studies have dealt with two classes of sounds, speech and others, with few studies targeting multiple classes of sounds, such as environmental sounds. Although environmental sounds might be segmented by extending this method to multiple classes, event length and frequency components might vary greatly from class to class, which may degrade performance. Additionally, state-of-the-art method CRNN has used RNN layers requiring extended computation time. Then we proposed mask unit, which consists of sound event detection block and segmentation block. This slide shows the complete architecture of mask unit, which aims to solve these three issues. For the accumulation of errors, we configured the proposed method as one neural network. For the imbalanced size data, we applied sound event detection block to the network. For the computation time, we configured proposed network without using RNN layers. Firstly, SDFT was applied to the mixed waveforms. SDFT coefficients were decomposed into magnitude and phase spectrograms. The amplitude spectrogram was input into the SED block, which outputs the sound event section. The output of the SED block was concatenated with the mixed sound spectrogram and input into the segmentation block. This block predicts the mask spectrogram for separating each class from the input spectrogram. The network should be able to learn the network efficiently because it is aware of the length of each sound event. Finally, the time domain signals were reconstructed using inverse SDFT. The difference between the conventional unit and our model was defined as the SED block. This structure is considered to be robust to differences in sound event size among classes. I will explain the details of each block from the next page. After the feature extraction using SDFT, the amplitude spectrogram was input into the CNN-based sound event detection block. This block estimates the probability of occurrence of each class for each time frame. Specifically, SED block had 9 convolutional layers, except for the last layer, 3 by 3 sized kernels, relay activation, frequency max pooling, and batch normalization were used. To maintain temporal resolution during frequency pooling, max pooling was not applied in the time direction, but only in the frequency direction. The final layer used one-by-one sized kernel and sigmoid activation. The loss function was binary cross-entropy. The output was post-processed because the SED output and the mixed sound spectrogram differed in dimensions. Specifically, the output of the SED was a vector indicating the presence or absence of each sound event at each time frame, whereas the mixed sound spectrogram was a matrix with both time and frequency dimensions. The output vector of SED was expanded to have the same dimensions as the mixed sound spectrogram. The SED output was regarded as prior event size information and input into the subsequent segmentation block. The output of the SED block was concatenated with the mixed sound spectrogram and input into the segmentation block using 6-layer unit. This block predicts a mask spectrogram for separating each class from the input spectrogram. The unit used in this study consisted of encoder and decoder blocks. The encoder layers used 3 by 3 sized kernel, stride 2, a leaky rel with a negative slope of 0.2, and batch normalization. The decoder block used 2D convolution layers with a kernel size of 3 by 3 and stride 2. There were 3 decoder layers with a dropout probability of 0.5. UNet also had a skip connection between layers of the same hierarchical levels of the encoder and decoder blocks, allowing low-level information to flow directly from high-resolution input to high-resolution output. The final layer used sigmoid activation. The loss function was the MSE loss between the target sound and the masked input spectrogram. Each of the three issues explained earlier was evaluated using the following indicators. For the error accumulation by the cascade method, we compare the proposed method with the baseline calculating RMSE. For the imbalanced size data, the RMSEs were compared for the average sound event size of each class. Specifically, the number of time frequency bins with a volume greater than 0.1 was defined as a spectrogram size. This was done to remove the slight background noise from the target sounds. For the computation time, we measured the inference time under the same conditions as possible of RAM usage and temperature. This page shows the experimental settings for the numerical simulations. 3 dry sources were randomly selected from these 10 corpuses, and the impulse response was convolved, like this mixed spectrogram. Then, diffuse noise were added to all time frames. We created 10,000 training set and 1,000 evaluation set. This page shows the results of the evaluation experiments on the three items explained earlier. This table shows the computation time and RMSE of the baseline and the proposed method. We used music plus GHDSS plus CNN as a conventional cascade method. The combination of these algorithms has been reported to be a robust method for noise and is a general framework for robot audition. The baselines for integrated methods used UNet and CRNN. Comparing cascade method and integrated method, RMSE was lower for the deep learning based integrated methods than the cascade method. Even if the accuracy of section detection and sound source separation is high, incorrect classification of the last block is calculated as a large RMSE. As a result, it is considered that the RMSE of the cascade method was the largest in this experiment. Comparing the proposed method with CRNN, the RMSE of the proposed method was the smallest, and the computation time was also less than half of CRNN. And compared to the UNet, the computation time was a little bit longer due to the addition of the SED block, but it improved the environmental sound segmentation performance more efficiently than adding RNN layers. This chart shows the relationship between sound event size and RMSE. The horizontal axis represents the sound event size. The green line indicates the performance improvement between the baseline and the proposed method. The reduction in RMSE was particularly large for large or small spectrogram size, because spectrogram size can be efficiently determined by the SED block. These figures show examples of segmentation results which were displayed as a single spectrogram colored for each class. Overlapped sound sources are displayed in different colors. The left, the left shows the ground truth and the others show the result of conventional unit and proposed method. This example contains a large-sized spectrogram shown in gray, but conventional method was unable to correctly classify large sound event size, whereas the proposed method could correctly classify large-sized spectrogram. Finally, this paper proposed mask unit as an environmental sound segmentation method for simultaneous section detection, sound source separation, and classification. Simulation experiments using a created dataset showed the proposed method can be segmented with high accuracy because, unlike conventional cascade method, errors do not accumulate. Compared with the deep learning-based traditional method, large spectrograms showed particularly high performance. Furthermore, because this method uses no RNN layers, its computation time was shorter than that of the state-of-the-art CRNN method. Thank you for your attention.